When we start talking to somebody, that discourse naturally starts with greetings. For instance, we say Assalamu alaikum and expect Wa alaikum assalam. Or, for instance, if somebody from the West would say hello, would expect a hi. This is the most intuitive form of conversation that we are accustomed with. In this module, we shall see a basic protocol for channel access that is based on hello kind of protocol called Aloha. Aloha is a Hawaiian word that literally means hello. In this module, we shall see what is the basic idea of Aloha, what do we mean about transmitting packets on Aloha, and if collisions do happen, what is the overall success of Aloha? We have to understand that this protocol is one of the simplest protocols which form the basis of medium access control sublayer. These two are the references, especially the first reference by Anurag Kumar analyzes the performance of Aloha and its variants in due detail and provides good mathematical foundation so that you can understand the strength and weaknesses of Aloha. The basic idea, as I said in the beginning, is to say hello, or in other words, just transmit as and when you like. It is, of course, based on the random access protocol mechanism that employs little or no intelligence. Since no certain restrictions are there on who is transmitting, when is somebody transmitting, and for how long somebody is transmitting, it is very easy to implement. It does not need any kind of pre-coordination between all the participating nodes in a network. Let's look at this figure to understand how Aloha is implemented and what are the vulnerabilities and strengths of it. Again, this is a time and space plane. Let's look at the top first. We have a node, node A. It is at a distance of d from node B. So the time it takes from A's transmission to reach B would be dependent upon what is the transmission time for the data that A is sending. That's the first thing. The second thing is what is the distance d in terms of the propagation delay. So let's look at the pointed arrow that marks the transmission start by A. The oblique packet is actually showing the time it takes to transmit the packet depending upon what is the data rate available on this network. When the node transmits, it takes a while before the reception starts to take place at node B, shown to you through the pointed arrow again on the line below. It starts getting received at R1 and the reception continues till R2. The total time that has elapsed since A started transmitting till B started to receive is shown by eta. Now, an interesting relationship exists between all of them. For instance, if the propagation delay is dominating, which means A and B are at a very large distance from each other, and someone else tries to transmit in the same duration, while A's transmission has not reached B, an accident could happen. Similarly, if A is transmitting to B and A's transmission has not reached B, there is a probability that B decides to transmit to A. So two transmissions would be on the wire at the same time, and eventually a collision is going to happen somewhere at distance d by 2. Let's look at the probability of any success, if at all, in Aloha. For that, we'll have to consider a node transmitting frame, say node I frame shown to you in yellow. If this frame is to be successfully delivered, say from node A to node B, in that case, what we strictly require out of the situation is that when the frame starts to transmit, there is no previous transmission before that which overlaps with this new transmission. And when this frame is being transmitted and also getting propagated over the network, no one else attempts to transmit in this duration. What we understand is that we do not want the leading edge and the trailing edge of this frame to collide with any previous or fresh transmission. So what we say is that probability that there is a success by a node is that the node transmits, of course, and no node transmits in the preceding time slot and in the subsequent time slot. In terms of mathematical representation, if the probability of transmission for a node is P, then this has to be P only for this node, and it has to be 1 minus P for all the nodes in the network for the previous slot and for the subsequent slot. So we'll have an expression like P times 1 minus P to the power 2 into n minus 1. Now, if we want to understand what is going to be the maximum efficiency of Aloha, we'll have to take an optimum value of P and take n as very large number. So when we take it to the limits, we observe that we do get a value that is 18%. So we've just seen that without incorporating literally any algorithmic intelligence, we still have been able to get 18% success, and it's not bad at all. With some enhancements, we expect to take it further, and that is what the subsequent advanced versions of Aloha are all about.